Hi guys, welcome to lesson 4.06 in the electron configuration chapter, or electrons and their location chapter. Today we're talking about sublevels and orbitals, and we started to touch on these different shapes in the last video. So before we go ahead, you might be wondering, well, how do scientists figure this out? You can't take a microscope and zoom down to the atomic level and take a picture of um, the electrons popping in and out of existence. Well, it turns out they predicted this mathematically. I'm not going to test you on this, but I think it's a good thing to talk about. So I am going to jot it down. I'm going to jot it down here at the bottom of the paper so it's kind of out of the way. We have something called the Schrodinger equation. Named from the guy who came up with the who discovered it. And it puts in parameters for electrons. And what it does is at the end, it spits out four numbers. So for example, if I solve the Schrodinger equation for a specific electron and a specific element, it might say 2, -1, nope, sorry, that would be +1, -1, +1/2. And you might be thinking, well, that's kind of a big leap to go from here to all of this complexity. Well, the first number is the main energy level. So this is the main energy level. And we've talked about that. That's the distance from the nucleus. So that was the equivalent of being in Grove versus Vaughansville versus Colida. The second number correlates to the orbital shape. In our analogy, we had a building or a house versus an apartment building versus a really more complicated structure like a nursing home. This is the direction that the orbital is turned. So the direction of the orbital, and I'm kind of writing this out of the way because you don't need to know this for the test, but I know some of you might be wondering it in your head. The last number is the direction the electron spins. So electrons could spin either clockwise or counterclockwise. And for two electrons to occupy the same orbital, they have to spin in opposite directions. So we use that as either a positive or a negative. So let's get into this second number, the orbital shape. So there are, it can be a 0 through 3. There are 4 different possibilities for these orbital shapes. We have S, we have P, we have D, and not pictured on this paper are F orbitals. So F orbitals, we're not going to discuss F orbitals. F orbitals are the fourth shape that we're not going to talk about, so they're not pictured. We're going to just let those go by the by. So remember, an orbital is a probability map. It's a probability map. You can't think of this as a fixed candy coating shell around an M&M. And we'll make this 1s orbital red. I don't know if that's going to show up red. But you'll notice there's a dark ring and a light ring. The dark ring is actually the orbital. So s orbitals are spherical. So that electron is popping, here's the 1s blown up, it's popping in and out of existence. Oh, boop, it's there, it's there, it's there, it's there. And if we drew a geometric map of that, it would look like this. This is the area where that electron's popping in and out. And at main energy level 1, when n equals 1, we only have one orbital. So the only orbital we have is a 1s. It's a super easy energy level because that's all there is. Now look at what happens. Here's our 1s again in red. The next orbital is the 2s. So we start over and we get an s orbital again, and I'm going to do that in dark blue. So this dark blue is the 2s. Then I go to, if we're just talking about s's, I'll have a 3s orbital as well. But again, they're always a sphere. All right, so let's take this, let's jump up to the n equals 2. So let's go to n equals 2. And we did that in blue, so I'm going to keep it in blue. N equals 2 is where we first start to get p levels, but we don't start off with a p level. So we have a 1s, and then existing around that, we have our 2s. And they fit one inside the other, and all the orbitals do this. They, if you've ever seen Russian nesting dolls, the smaller doll goes inside a larger doll, goes inside a larger doll. So the 1s fits inside the 2s, and then we get these 2p. And here's all of the 2p, but they're a little bit hard to figure out what's going on. So what they did was they split out the 3 different 2p orbitals. So p orbitals have a dumbbell shape, or a figure 8, or an hourglass. Some people say it's the infinity symbol. And one is oriented around the x-axis in space, one is oriented around the y-axis in space, and one is oriented around the z-axis in space. So this number down here, n equals 2, has got to be one of these 4 orbitals. Well, it's a 1, so that tells me that it is a p, because the number p correlates to 1. And it's the -1, so that would tell me we're talking about this orbital right here. This orbital is going to hold 2 electrons. One's going to spin this way for +1/2, and one's going to spin this way for -1/2. So I would be talking about 2, +1, -1, 1/2 is talking about this electron right there. So that's how these numbers correlate to a specific electron. And we're going to talk about, actually, I'm going to talk about it here because I'm not sure if I put it in the other videos. The Pauli exclusion principle. Says that every electron must have a unique set of 4 quantum numbers. Well, those 4 quantum numbers are here, but it correlates to a region in space and the probability of where an electron is going to be. So let's talk a little bit more about n equals 2. So this is going to be, at n equals 2, I've got my 2s. This is my 2px. We call this 2py. This is 2pz. So each one can hold 2 electrons. So at n equals 2, I can hold 2, 4, 6, 8 electrons. And they're found in each of these unique orbitals. Remember, this is just a combination of the 3. Well, what's going to happen when I go to D? When I get to, when I get to n equals 3. And now we're talking about n equals 3. Can you guess? Well, you had a tip off up here. So they're showing the s orbitals. And now look, I've got a 3s. So I start off and I have a 3s orbital, which is a sphere. And then I have p orbitals in n equals 3. I have 3px, I have 3py, and I have 3pz. Whoops, z. And they would have the same orientations. Is what we saw over there. But now I have d orbitals. D orbitals have kind of a flower shape. And there are 5 of them. Now the shapes are getting weirder and the orientation is getting weirder we have the names are 3D X2, 3D YZ, 3D, can't even read it, 3D XY, 3D X squared Y squared. So it's getting really crazy. You don't need to know the shapes, you don't need to know the names, but you see how they're oriented in different directions. So n equals 3 would be the first quantum number. And then if I had a 0, it would be here. If I had a 1, it would be here. If I had a 2, it would be here. I hope those are the right ones. I think it's 0, 1, 2, 3. But even though these have 4 little lobes, that doesn't mean they can hold extra electrons. We still have, each one can hold 2 electrons. So this is the orbital diagram notation for these. And remember, these guys can hold 2 electrons. So if n equals 3, what's my total number of electrons? I can do 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 electrons maximum. And you have to be able to answer questions like that. So if we say, how many electrons can n equal 2 hold? That would be 8. If I say, how many electrons can the p orbitals in n equal 2 hold? Well, there's 3 p orbitals in n equals 2. So that's 2, 4, 6. Now, it's all a little bit confusing at this point, and what I tell students is give it time, and I'm going to give you some shortcuts, but I'm not going to give you the shortcuts until the last video, because we need to understand that these are probability maps, so that they have specific shapes. I want to do a video clip that I think really helps, because it shows how the electrons build and how they nest. So I'm going to go to that now, and I'm going to share my screen. Share. Next screen. So we're going to look at the electron, play this. I think it's playing, here we go. These are the orbitals for scandium, which has 21 electrons. So the first 2 electrons in scandium exist in the 1s orbital. The nucleus is at the intersection of the 3 axes. So after the 1s orbital, the next 2 electrons are in the 2s orbital, because at the first energy level, we only have 1 orbital. Now we're in the n equal 2, so I've put the n, the 2s, here comes the 2px, and then I do the 2py. So I'm now at electrons 6 and 8, and electrons 9 and 10 are going to be in the 2pz. So far, here are 10 of my electrons. That makes sense. We said the first energy level has 2, second energy level has 8. Now I start with the third energy level. Here's the 3s. That's going to follow with p's. So I'm going to do my 3px, and notice it's further away from the nucleus, because we know that n equals 1 is closest, n equals 3 is going to be much further away. And even though it's the third energy level, the p orbitals orient themselves in the same way. What comes next? Well, maybe you're saying, here come the 3Ds. Okay, we've got a hiccup. So there's a reason why it goes to the 4s first. I'll explain that later. The 4s is actually a little more stable. So the Ds actually come in after 4s. Don't worry about that now. But here come those weird shaped Ds. And I'm going to have 5 of those. So those last few electrons are going to fill in those d orbitals. And we have those funky names and the funky shapes. But even though it looks like 4 balloons tied together, it still only holds 2 electrons. And here's the last one, I believe. But every element fills the same way. It always goes from the lower energy up to higher, the closer orbitals up to the further, into the orbitals that are further away. All right, go ahead, pause. And I'll stop sharing my screen. So what are our takeaways today? Our takeaways are that these probability maps have specific shapes. And remember, it's not a fixed orbit, it's a region of probability. And the scientists figured it out mathematically. It comes from this crazy equation. We have 4 shapes, but we talked about 3 of the 4. So the f orbitals we're leaving off the books today. S orbitals are a sphere. P orbitals are a dumbbell, hourglass, infinity, whatever you want to call it. And the D orbitals have this flower shape. At n equals 1, all we have is an s orbital. At n equals 2, we have an s and we have 3 p's. And then we get to n equals 3, and there we have an s, we have 3 p's, and we've got 5 d's. And this is pretty much where we're going to stop. We'll play around a little bit with some of the n equals 4 and n equals 5, but we're leaving these off the table, so we're not going to go above, much above this. All right, that is our, oh, and most importantly, when we say the word sublevel, I never defined it. My goodness, shame on me. We're talking about the orbital shape. So at the n equals 2, we have 4 sublevels, or we have four levels. So let's add that to the notes before we wrap things up. Sublevel, so if it asks in your homework, what are the sublevels for n equals 3? They're asking what are the orbitals for n equals 3. So you could say the sublevels for n equals 3 is the 3s, 3px, 3py, 3pz, and then the 5 3ds. So that's why this is sublevel / orbital. All right, I think that takes care of all we needed to do. Thanks for watching. Have a good day.